Well, hi guys, I wanted to do a couple of quick examples of finding derivatives. And before I do, let's review what our derivative means and how we compute it. F prime of x means three things. It means, first of all, physically, the instantaneous rate of change. Of f with respect to x. Second of all, geometrically, it means the slope of the line tangent to the graph of f at point x. And third, it is the limit as h goes to 0 of f of x plus h minus f of x all over h. Today in class, we introduced an alternate form of computing the derivative. If I compute the derivative at point C, then I can write that as the limit as x goes to C of f of x minus f of c all over x minus c. So if you're thinking in terms of definitions and theorems, these are the definitions that you really want to know. And if you are wanting to distinguish between these two forms, to help you remember them, it's easiest to draw a graph of a function f, mark a point x, mark a point x plus h. What is the slope between these 2 points? Well, as soon as I draw x and x plus h, then I have f of x plus h, and I have f of x, so that the delta y, the distance between the y coordinates, is f of x plus h minus f of x. The distance between the two x coordinates here is h. And to make all this instantaneous, we let the denominator go to 0. So this is the basic way that we can remember these by constructing the slope between the points and letting our denominator go to 0. Okay, that's our theoretical material. Now, to take an example, let's consider let g of x equal the square root of x. And let's find the derivative g prime of 9, like so. And we're going to do this first by using the definition of the derivative, and then we'll come back and use the alternate definition and see how that works out. If I use the definition of the derivative, then I would say that g prime of 9 is the limit as h goes to 0 of g of 9 plus h minus g of 9, all of that over h. And that is my difference quotient set up. Now that I've set up the difference quotient, I can substitute into it. And when I substitute, because g of x is equal to the square root of x, g of 9 plus h will be the square root of 9 plus h. And g of 9 will be the square root of 9, which is, of course, 3. And all of that is divided by h. At this point, the substitution is done. The only thing left is to evaluate. And it looks to me like this evaluation is best done by a rationalization technique. I can multiply top and bottom by root 9 plus h plus 3, root 9 plus h plus 3. And when I do, on the top I get 9 plus h minus 9 all over h into root 9 plus h plus 3. 9's cancel, leaving me with a factor of h in the top, a factor of h in the bottom. H divided by h is 1. And if I now let h go to 0, I get 1 over 3 plus 3, or 1 over 6. And so g prime of 9 is 1/6, found with the definition of the derivative. Let's look at what this would have looked like if we had used the alternate definition instead. Using the same function and the same point of tangency, c equals 9, we can say that g prime of 9 is the limit as x goes to 9 of g of x minus g of 9 all over x minus 9. And this is our difference quotient step. And just check really fast that what we're doing here is y2 minus y1 over x2 minus x1 to get a slope. And then we are taking the limit of that slope to get an instantaneous rate of change. Now that we have the difference quotient set up, we do a little bit of substitution. G of x is root x, and g of 9 is root 9, or 3. And it looks to me like this is also a good candidate for rationalization. And so we rationalize. And we do. On the top we get x minus 9. At the bottom we have x minus 9 times root x plus 3. And these factors cancel, giving me 1. And if I now let x go to 9, I get 1 over 3 plus 3, or 1 over 6, just as we did in the other definition. I hope this is helpful to you in seeing how we set up these problems, and I'll see you tomorrow.